So this is a kind of an interesting image, okay, or kind of an interesting scenario. So we've got a smaller wrecking ball in the middle, and then a big wrecking ball at the end. Oops. Okay, and so we've got two different sections of our cable. When it says the mass is ignored, it means just the mass of the cable is ignored, right? The cable is so lightweight in comparison to these wrecking balls that we don't have to take that into account for our system. So we've got two different areas that we have to pay attention to. We're going to look at what's the tension in this section of the cord and the tension in this section of the cord. So we're going to have two different problems that we need to do. Okay, two different problems. We can't do them in the same problem. So let's just start with the top first. Okay, so let's start with the whole top system first. And I'm going to draw kind of a free body diagram here for my top system. Can you see that pink over the top or no? Okay, so here I've got gravity pulling my object down. And then what's my upward force here? It's through a rope or a cable, so we call it tension. So I've got a tension force here that's holding my object up. And that's it for our free body diagram. There's nothing pulling us one way or the other, right? Side to sidewise. So if I were going to go set up for the top section, my net force equation, what's my net force equation here? Positive forces minus negative. So what would be my positive force here? Tension minus F what? G, right? My gravitational force is my downward force. So here's what I want you to think. Can you guys see that pink okay? Or is it too hard to see? It's okay? Okay. So here's what we need to be thinking about here. Tension is what we're solving for, so I'm going to leave that. The force of gravity can't just take into account this wrecking ball. It has to take into account everything that falls beneath it. So when I'm looking at my FG, I would say the tension force minus the mass times gravity, right? Because isn't the way I solve for FG to take mass times gravity, right? Or mass times 9.8 on Earth. That's how I solve for FG. But I have to take into account all of the mass that hangs below it. So the 1,200 kilogram and the 7,000 kilogram. Both of those have to be taken into account. That's also true over here for the F net side. So I would say 8,200 times the acceleration of my total system. Acceleration of my total system, which they told me was 2.10. Is my acceleration going to be positive or negative? Negative. It says it's lowering the system. So it's moving downward at 2.10 meters per second squared. So negative 2.10 would be my acceleration. So I'm going to move that around to solve for my tension. So F net, I substituted in MA. And FG, I substituted in MG. You see how that worked out? Right? I'm going to do that math. I can do it ahead of time if I want and then pull the number in. Or I can just do it in one equation. So this gives me negative 17,220 equals tension minus 80,360. And so then I'll move that to the other side. And I get a tension force equal to about 63,140 newtons, right? All I did is subtract, I added this one to the other side, and that gave me a positive tension value. Would it be a red flag if we came out with a negative tension value? Yeah, because our force is going upward, right? So it would be a red flag for us if that came out negative. Okay, so that's the amount of tension in the top portion of our cable. But it asks us for the tension in both sections. So now I'm going to start working on the lower portion. And my equation will look exactly the same, except the difference is I'm not concerned with the top one anymore. I'm only concerned with what hangs below it. So FG and FT for this second one, that blue. Okay, I would say F net equals my tension force minus my gravitational force. But what's my mass going to be here? Only 7,000. So I'll take 7,000 times negative 2.10 equals my tension minus 7,000 times 9.8, right? And it's going to give me a lesser tension in that bottom one. Because it tells me my system is being lowered, so it's moving in the downward direction, so my acceleration is negative. If it was being lifted, it would be a positive 2.10. So I got about 53,900 newtons. Okay, so when we're looking at hanging things, our gravitational force is always concerned with whatever is hanging below it, however many objects that is. So we've got to take that into account, whatever is hanging below that object. There's two main types of friction, kinetic friction and static friction. What's the prefix kina mean? When we talk about kinetic, what's kina? Motion or movement. So kinetic friction is friction that acts opposing the direction of an object's velocity once the object is in motion. Okay, so kinetic friction is talking about objects that are in motion. That's really, really important. If an object is in motion, it cannot have kinetic friction. Okay, the magnitude of any frictional force and kinetic friction specifically depends on the nature of the two sliding surfaces. So if you have like a marble on ice, are we envisioning much friction there? No, but if you have a carpet on wood, are you envisioning friction there? I would say so, right? Carpet on carpet would be a lot of friction. Rough surfaces tend to lead to friction, an increased value in friction. Okay? Kinetic friction has a relationship that's proportional to the normal force. So let's review, what is the normal force? Tell me what the normal force is. That's right. It's force of the surface exerted upward on the object. So if I've got an object that's sitting on some sort of surface, right? Gravity's pulling that object, but the normal force is holding it up. So the normal force is exerted upward on an object. When I lift up on an object, if I tried to pull the object up, am I relieving the normal force or am I making the normal force work harder? I'm making the normal force work less, right? If I try to lift this up, if I apply a force that tries to lift it up but it doesn't leave the table, the normal force has to work less hard than it did before. If I push down on my object, what's the normal force have to do? Has to work harder, okay? So when we're talking about friction, we're talking about the relationship with a normal force. So I want you to put your hand on the table. Just lightly rest your hand on the table and slide it back and forth. Fine? Not too difficult, right? But what happens if you push down and try to slide? What happens? It becomes more difficult, right? Friction has a greater impact when the normal force is greater. So when I push down on my object, my normal force has to work harder. And so friction becomes more intense, right? You could also think of it as those surfaces are interacting a lot more, right? The heavier an object is, the more it's pushing down on that surface, the more that my hand is having to interact with the surface of the table, right? It becomes more difficult. So here is our equation for friction. The force of friction, and any force of friction here, kinetic or the other type, but force of friction is equal to, this little guy right here is a Greek letter, and it's called the coefficient of friction, okay, times the normal force. So the frictional force of any object is equal to the coefficient of friction times the normal force. Now, the coefficient of friction is dependent upon the two surfaces that are interacting. So we'll have a table of coefficients of friction that have been measured. So it might say wood and wood, right? And it would give a coefficient. Or it might say steel on steel, and it would give a coefficient. Or it'd just be given to you in the problem. But that coefficient of friction, something that we should know about it is that it doesn't have units. It has no units, because if normal force is measured in newtons and frictional force is measured in newtons, it doesn't leave a unit for us. Okay, so coefficient of friction has no units. Okay, no units. And traditionally, our coefficient of friction is less than 1. It has a value of less than 1. Okay, so if you get a coefficient of friction with a value of 300 something, right, you did something wrong. Okay, typically, our coefficient of friction comes out at less than 1. I would draw the line at less than 2. Okay, very rarely will we have a coefficient of friction that's greater than 1. But I'm not going to say it's impossible because sometimes I make up problems. Okay? All right. Second type of friction is called static friction. What do you think that probably means? What's it mean for something to be static? It's not moving. It's standing still. So frictional force of an object when it is at rest. The static frictional force has to be overcome if we want to put an object into motion, right? If I want to put this object into motion, I've got to apply enough force to overcome the static friction and then to put it into motion. Okay, so if I don't apply enough force, it's not going to go. I've got to overcome my static friction and then put it into motion.
Why is it not like stagnant?
What do you mean?
Like, isn't static like when you rub a balloon on your hair and
Static can mean a couple different things, but if you think about you mean use the word stagnant instead of static? I don't know. Yeah, I don't know. Okay, same equation for frictional force. Tell me this, which value should be higher between the two coefficients, the coefficient of static friction or the coefficient of kinetic friction? Which would you envision is going to be a higher value? Static friction. I would agree. It's harder to get something going than to keep it going. You know what I'm saying? It's harder to put something into motion than to keep it in motion. So once an object is in motion, kinetic friction is less. Static friction is more. Okay, it says page 183 has a chart with values. I'm not so sure about that. We'll look at values later. Okay, so let's just try a problem here. Okay, your sheet might have all the steps written out for you, but I'm going to give myself some room to work here. It says a sled has a mass of 50 kilograms and is pulled horizontally along a flat, snow-covered surface with a force of 75 newtons. The coefficient of kinetic friction is 0.010. Does your slide have a bunch of different things marked off for you? Okay, I'm going to leave those out. Our overall goal here is to find the horizontal acceleration. That's the very last bullet point. So that's overall goal. What is the horizontal acceleration for our system? First thing we have to do is draw our free body diagram. So I've got my sled. It has to have gravity. And what has to offset gravity? Normal force. Okay, in this scenario, is my sled moving vertically at all or accelerating vertically at all? No. And so what do I know has to be true about those forces? They have to be congruent. Okay, that won't always be the case, but in this scenario, there's nothing else happening vertically. Their only vertical forces are normal and gravity, so they have to be equal. Then it tells me my sled is being pulled horizontally, so it's not being pulled at an angle, it's just being pulled horizontally with a value of 75 newtons. I'm just going to call that applied, right? Force applied is 75 newtons. It tells me a coefficient of friction, so that means I have to have a frictional force. Okay, we've got to draw the frictional force if it gives us a coefficient of friction. Okay, do you feel okay about drawing that diagram? Okay, so my overall goal, we said, is to find the horizontal acceleration. So let's just start with that. So in the x direction, my net force would say F net equals what? What's my positive forces here? 75, or I'm just going to write it with the variables first, but force applied minus force of friction, right? Positive forces minus negative forces. Now I'm going to start putting in some numbers, okay? What can I always substitute in for F net? Mass times acceleration. So my mass is 50. My acceleration, I don't know. That's what I'm solving for, right? That's the overall goal. My applied force, we said, was 75. My frictional force, I don't know it. But what's my equation for my frictional force? Frictional force is equal to what? Coefficient times the normal force. Okay, so I'm just going to put in what I have. I know so far that the normal force, is 0.01. The coefficient, not the normal force. I'm going to leave normal force for right now because I don't know it yet. I don't know it yet. That's all the information that I know. Would you agree with that so far?
Isn't it just 9.8?
What is 9.8? Nope. This Fg is mass times 9.8. Right? It's not just 9.8. Fg is the weight, so it's got to be mass times 9.8. So that's right. To solve for my normal force, since I know, I'm going to come down here to the bottom here. Since I know that my normal force and my gravitational force are equal to one another, I can just plug that in. So Fg is equal to mass times 9.8. And so that would give me 490 newtons would be my value for my normal force. So that's what could come in here. Right? That is only true because I have no other vertical forces acting. If I was pulling on my object at an angle, I would not be able to make that assumption that the normal and the gravitational force are equal. That won't always be the case. But in this scenario, it is, right? Because I don't have any other vertical forces acting. So I'm going to go ahead and sub that in here for my normal force. I'm going to say that that's equal to 490. Okay, so now I can just go ahead and solve for A. Okay, so
if it's purely horizontal, your normal force and gravitational force would be right.
Yep.
Always.
As long as your object is not accelerating in the vertical direction, those are going to be equal. And as long as there's no like third weird force happening, right? If we're not pulling on it vertically. Yep. Okay, so let's see what that looks like. 75 minus 4.9 equals 50 times A. So that gives me 70.1. And that gives me an acceleration equal to about 1.4. A crate is pulled horizontally with a force of 710 newtons. If the crate moves at a constant velocity, what is the coefficient of friction? What's the coefficient of friction? That's what it's asking for this time. So let's draw our diagram first. It's going to look very similar to the last one, isn't it? Yeah. Right, we've got gravity. We've got a normal force. It says it's pulled horizontally. We're going to assume that it's being pulled in the positive direction, although it doesn't necessarily explicitly say that, but we're going to say it does. And what does it mean for us when it says it moves at a constant velocity? Acceleration is 0. What's that mean about our frictional force here? It's congruent. Okay, so let's look at this. Those two forces are congruent, but does it necessarily mean that they are congruent with gravity and normal? No. So here's the deal. We know that our frictional force and our applied force are congruent. We also know that our normal force and our gravitational force are congruent, but they are not congruent to one another. Okay, do we feel okay about that? You don't have to draw the congruency lines. I think it just speeds up the process a little bit, right? It makes it a little bit quicker. All right, so it says, what's the coefficient of friction? Does that mean we're focusing on a horizontal or a vertical? We're looking at the horizontal. So let's look what that looks like. Net force is equal to applied minus force of friction. We already said the net force is 0 because it's moving at constant velocity, which means my 75 minus my force of friction. So we already knew without even doing this that my frictional force was 75. I don't know. 710. Sorry. Was it 75 in the last problem? Okay, sorry. That's why. All right, so that means my frictional force is equal to 710. Could you have done this step without even writing out that equation? Yeah, because you knew that they were congruent. That's fine with me. So, but that's not our answer, is it? It asks for the coefficient of friction. And so if my frictional force is equal to coefficient times the normal, I've got to solve for what my normal force is, right? 710 is equal to my coefficient times my normal force. Okay, so how can I solve for my normal force? Solve for Fg, right? Because I know that those two are equal. So let's come down here, do that also. Fg is equal to mass times 9.8. And that gives me 2,205. And so I'm going to plug that in for my normal force. And then how am I going to divide that over? I know, but are you going to divide the right way? 0.322.
Oh yeah, you just divide by 2,000.
Yep, 710 divided by 2,205 and gets me that coefficient. Okay, so do you see how you can reason through some shortcuts there, right? You can always set up the equation if you want. It works, right? But if you know that constant velocity tells you that those two are equal, that speeds it up just a little bit. Okay, so you're welcome to do that. With a force of 100 newtons at 40 degrees, the box begins to slide. It begins to slide despite that the coefficient of kinetic friction is 0.30. So now what's the problem? What's different from this problem than the last ones? Pulling it at an angle. Okay, so let's draw our diagram. Oh, quit sighing about the diagram. It's not that big of a deal. Fg, we've got a normal force. We've got an angle, a force applied at an angle here. So this would be, I would call that, let's see, is it 100? Okay, I call that one force applied. But can I use it if it's at an angle? No, I've got to break it into, what did I call these ones? Do you remember? Force applied Y and force applied X. And then I've got one more force here that I'm missing. What do I have to include? Friction. So would friction go at an angle like that? No, it just goes on the surface, right? Force. What do you mean? How long you draw the friction?
I kind of thought the thing didn't take flight, so friction wouldn't matter.
No, it just slides. See, it says it slides.
Pulled at a 40 degree.
Right. She's dragging it. Right? But it's still sliding. Okay? So how do we feel about the diagram right there? Can we do that ourselves? We'll see. Okay, so are we going to need both applied X and applied Y?
Yeah. Yes.
I think we will. Why do you think, just help me think about why are we going to need applied Y? Because that's the one I think you guys are thinking we're not going to need. But tell me, why do we need it? I have to use it to help me solve for Fn. Because in this case, Fn and Fg are not congruent because I've got 3 vertical forces happening. Okay, so we're going to take that into account later. But since we know we're going to need applied X and applied Y, let's just go ahead and solve for those now. Okay, so for applied Y, I'm going to use sine. So 100 times sine of 40 gives me 64.3. And applied X gives me 76.6. So I'll never use the 100, right? I'm not gonna put that in anywhere. After I've broken those down and solved for them, I'm done with that. Okay, so my overall goal is to find horizontal acceleration. Before I do that, what do you know that I'm gonna have to have? If I've got the coefficient of friction, that means I'm going to also have to have the normal force. So let's just do that first. Let's solve for the normal force first. Okay, so actually we're going to start with vertical stuff here. If I need the normal force, I'm going to start with my vertical. So I'm going to go F net equals my normal force plus F applied Y minus Fg. Right, I've got my upward forces. They're both positives, right? I'm adding both of those in, taking out any forces that are going in the negative direction. Okay, are we feeling okay with that so far? Okay, what's my vertical net force?
64.
Nope, it's 0. Is my object moving vertically? Is it accelerating vertically? No, so that's the tricky part. We've got to be able to separate vertical and horizontal. So vertically, my object is at rest, right? So my F net would be 0. So my applied y is 64.3.
Pulling up on it. How is
It's
it?
going up.
It's sliding.
It's not.
It's not lifted. It's slide. Yeah, like there you go. Right. It's sliding.
But then how is it at an angle? She's standing.
She's
and her
pulling
feet
at an
are-
angle. It'd be like me doing this.
Down.
You know what I'm saying? I'm pulling upward, but it's not enough to lift it off the ground. Right? It's just
It's
sliding.
just two head.
Yeah. All right. How do I solve for FG? FG should be like quick. Mass times acceleration. So I'm going to take 30 times 9.8. And then I'm just going to solve for Fn.
Gonna be that negative.
Do you think it's going to come out negative?
No.
We don't want our normal force to be negative. That would be a red flag. Fn minus 229.7 equals 0. So what am I going to do?
Add that over.
Just add that over. So my normal force is positive 229.7 newtons. Okay, do we see how that works? Bless you. This is a type of problem that is really kind of the most complex we're going to see, right? It involves us solving for something with the normal force and then using that value in a horizontal situation. Okay?
Still not even done.
We're not done yet. Yeah, probably. Do you want me to you want to do that one on your own?
No, I just don't have
You're right, Scott.
Okay. So for X, we're going to go F applied X minus frictional force, right? I've got two horizontal forces, one positive, one negative. Is my net force in the horizontal direction, is it 0? We don't know. It's not, right? Because we're looking for acceleration. So I'm going to take my mass times A. Yep, that was just the Y. 76.6 minus the coefficient times the normal force. So if you wanted to solve for the force of friction up here separately and then plug it in, you could. I just like to do it all in one equation, so that's really up to you. Okay, so let's see here. 229.7 times 0.3 gives me a frictional force of 68.91. So my net force is 7.69 equals 30. A, and so my acceleration is equal to about 0.256 meters per second squared. Say it again. Uh-oh.
What?
Try this one on your own.
Let's see if I can draw the diagram.
Let's draw the diagram. I would agree with that. I'll give you a 2-minute head start.
I'm gonna need a little more.
That's exactly it. No. Just think for just a second. My frictional force, or my net force here comes out to be negative 23.2 newtons equals 65 times A. So that's fine. But here's the thing. Does friction ever pull things backwards? Does friction ever by itself pull things in the negative direction? My frictional force is greater than my applied force here. So what's the solution? It does not move. My thing won't move. I'm not applying enough force to overcome friction at all. So a negative acceleration is huge red flag. Red flag, right? There's no way that friction alone can pull it backwards. It doesn't happen, right? My frictional force, 525.2 times 0.36 gives me 189, right? My frictional force is 189.07. So my frictional force is greater than my applied force, which just right there could have stopped your problem and said, no, it's not going to move, right? I am not applying enough force. So you guys were right in seeing that negative and knowing it's a red flag, right? Because it's no good.
If it's always negative, it won't move.
So if it had an applied force pulling it that way, it could work. But friction by itself never pulls things, right? Friction just slows things. So that should have been a red flag.
That's what I was gonna say.
Okay? Yep, no good.